In this example, we're told we have a centrifugal pump with a 12-inch diameter impeller. It requires a power input of 60 horsepower when the flow rate's 3,200 gallons per minute against a 60-foot head. The impeller is changed to one with a 10-inch diameter, and we're asked to determine the expected flow rate, head rise, and input power if the pump speed remains the same. So the idea here is this, that when you purchase a pump, you can get different sized impellers that go in the same casing. Okay, so you still keep the casing the same, but you can switch out the impeller to different sizes. In many cases, the manufacturer will provide pump performance curves for the different impeller sizes. So for example, you might see a plot that looks something like this. This is head rise versus flow rate. Here's the pump performance curve for a particular impeller diameter. But if they sell different impellers for the same pump, you might see different curves like this, depending on, this would be, these would be the different impeller diameters. Now, if they don't provide that information, and instead they only provide the pump performance for one impeller, kind of like what I've shown here, then we have to do some scaling. Okay, so to do that scaling, we'll rely on the flow coefficient, the head coefficient, and the power coefficient. These parameters come from the dimensional analysis associated with pumps. This is covered in the notes. So the dimensionless flow coefficient is defined as the volumetric flow rate divided by the rotational speed of the pump times the pump impeller diameter cubed. The dimensionless flow coefficient is defined, this is the head coefficient. This is G times the head rise divided by omega squared D squared. And finally, the dimensionless power coefficient is defined as the power going into the fluid divided by the fluid density, omega cubed, d to the fifth. So those are all dimensionless parameters related to pumps. It comes from doing a dimensional analysis of a pump. Okay, so it's something that was covered in the notes. So if we're going to do scaling, what we want to do is keep all of these parameters the same. So whatever this flow coefficient is for case 1, or system 1, it should be the same flow coefficient for system 2. We can do the same for the head coefficient. And we can do the same for the power coefficient. Note that if you keep all three of these the same between scales, then the pump efficiency should also be the same between scales, because you can form the efficiency from these different, the three coefficients that I have here on the page already. So if all three of these coefficients are the same, then the efficiency would be the same as well. All right, so in this particular case, we're told that the pump speed remains the same, so that means the omega is the same between the two different scales. Similarly, we'll assume that gravitational acceleration stays the same as well as the fluid density. So what that means then, for our particular case, is Q over D cubed 1 should equal Q over D cubed 2. H over D squared 1 should be H over D squared 2. And then the power over D to the fifth for case 1 should be the same as the power over D to the fifth for case 2. Or just doing some rearranging, Q2 is equal to Q1 times, let's see, that would be D2 over D1 cubed. For the head rise, it'll be the head for case 1 times D2 over D1 squared. And then for the power, for the second case, it'll be equal to the power for the first case times D2 over D1 raised to the fifth. So these are the relations we're working with here. And we can plug in the numbers. We're told the volumetric flow rate in the initial case is 3,200 gallons per meter, so that's our Q1. So let me just make a note of that. That's Q1. Our H1 is this. Our D1 is this impeller diameter there, so that's D1. And our input power, that's our W dot 1, is given as well. And we're going to change to our 10-inch impeller, that's our D2. Okay, so we can plug all those in, and when we do that, we'll get that Q2 comes out to be 1850 gallons per minute. H2 comes out to be 41.7 feet, and the power for this new impeller size is 24.1 horsepower. So these are the predicted values for those various cases when we're using a 10-inch impeller diameter. Now, this is the result we would get from a pure, dimensional analysis approach to this problem. Dimensional analysis is what allowed us to get to these relations. Now, one of the assumptions in dimensional analysis is that we maintain geometric similarity between scales, meaning that when we change the impeller diameter from one scale to the other, we should change all of the other geometry for the pump simultaneously. So technically, in order to use this dimensional analysis, we ought to also be scaling the casing diameter as well, right? But that's not typically done in practice. Instead, it's the same casing diameter, but we just change the impeller diameter. So we're not holding geometric similarity. We don't have perfect geometric similarity when we do this kind of scaling here. Okay, so what that means for us in practice is that the predictions that we get from this kind of scaling aren't entirely accurate. Okay, we're assuming geometric similarity, but there really isn't. So these kind of predicted values that we get from this, they get us in the right ballpark, but they're not entirely accurate. Now, what people have found is that they've done empirical scaling, basically through trial and error, have found that there is a different type of scaling that seems to work better in practice. It's just based on trial and error or empirical evidence. And that alternative scaling, when you're changing the pump impeller, is this. Let me write this down. This is the empirical scaling approach. And this is what this one's a little more accurate if you're scaling the pump impeller because of that issue with geometric similarity. So this would be Q2 is equal to Q1 over times D2 over D1 squared. So using pure dimensional analysis, it would be raised to the cubed. But empirically, raising it to the second power seems to work better. The head rise looks exactly the same. That one doesn't need to be changed. And then the power, instead of raising the diameter ratio to the fifth, turns out raising it to the fourth seems to work better. So if we use that kind of scaling approach, then you'll get that Q2 is 2,220 gallons per minute. H2 is still 41.7 feet. And the power for 2 is 28.9 horsepower. Okay, so again, this scaling approach is purely empirical. It's just found from trial and error, many different experiments. They found that this kind of scaling, when you're changing the impeller diameter, seems to work better. It's more accurate. And again, the reason this approach isn't as accurate is because we're not maintaining pure geometric similarity. So you can see, the flow rates are a little different. They're not too far from one another, but this approach will be more accurate than that one. Head rise is the same, and then the power is a little bit different as well. So this second one would be more accurate than this one, okay? But they're both still in the same ballpark. Now, if we were scaling just the rotational speed, so let's say the impeller diameter was the same. So we're going back up here. The impeller diameter is the same, but we're changing the rotational speed. Well, then we don't have to worry about geometric similarity. It's the same pump, okay? So in that case, this kind of scaling works really well. We don't have to switch to some empirical scaling. This works pretty well because we have geometric similarity. It's the same pump. We're just changing omega in that case. All right, so this is a pretty simple example showing how scaling is done with pumps when you're changing the impeller diameter, and I just described what you do if you change the impeller speed. And as I mentioned before, this kind of scaling is okay. It's not wrong. It's just not as accurate as using the empirical scaling approach given down here. This is a better model than this model. Okay, we'll end the example there.